Dear students, welcome to 7th lecture of this course. In this lecture, I am going to discuss parametric curves and with special emphasis on non-form curves. Let us start with the brief introduction of the geometric modeling, which already we have been discussing in the previous lecture. We discussed that geometric modeling is concerned with the representation of curves, surfaces, and solids. So we will be starting with the curves representation or the parametric modeling of representations. Let me tell you that parametric representation curves is the most popular form of representation as far as your geometric modeling software or CAD modeling software are concerned. So most of these softwares, whether it is SolidWorks, Wildfire, NX, Fusion 360, they make use of parametric curves to model their curves or to store that information about these curves. Let me discuss about the kinds of representation which are available for different kinds of curves, surfaces, and solids. Okay, the first kind of representation is the implicit representation, where you are making use of both the parameters or both the variables like x and y, and there is no distinction between x and y or the dependent and the independent variables. And this is actually when you have this kind of equation where both the variables are coming on the left side, say, and they're equated to 0, so mostly it is a implicit form of representation. And explicit representation is where you have a clear distinction between the dependent variable and the independent variable, as you can see in this equation. And on the other hand, parametric representation is in this representation you are notating both the different variables. For example, in this case, with respect of another parameter. Okay, so x is also with respect to defined with respect to u, and y is also defined with respect to u, which we call it as a parameter. So all of these equations, whether it is implicit, explicit, or parametric, this case, this is about the, as you are well aware that this is equation of a circle and this too is equation of a circle, and this is again equation which is representing a circle. We will see in a moment how. On the other hand, this uh, example is of implicit representation of a plane or a line. It may represent a line or it may represent a plane also. Here again, you don't have any distinction. If you see the equations, these variables, they are on the one side of the equation, and there is no distinction between dependent and independent variable. Here, in this explicit representation, you have a distinction between the independent and dependent variable. So x and y are the independent variable and z is the dependent variable. So when you have two independent variables, you need to provide two parameters to define. So this is typically representation of a plane. This too is a representation of plane, because you can see that there are two independent variables. So whenever you have two independent variables, so that means it is representing for such an equation, it is representing a plane. And here correspondingly you will have to use two parameters u and w to represent this plane, and again it is having three different equations, one each for x, y, and z. Okay, now let us discuss with the help of this example of a primary features of parametric curves or parametric representation. Parametric equations completely separate the roles of dependent and independent variable. For example, in this equation, this is you can answer these questions like what is this representation? What does this equation represent? X, Y, and Z are separately notated with respect to another parameter u. Okay, so when you have different cases of this parametric representation where you have equation of x, equation of y, and equation of z, which is equal to h. Now, let us discuss with respect with the help of different cases. For example, the first case, this is r is equal to 5, u is equal to 0.5, and h is equal to 20. So when you open up this equation, this is giving you one constant value of x, constant value of y, and constant value of z, because you see all the variables like r, u, and h. These are given with the help of some numbers. So that means the result of x, y, and z will be constant values. So if you are having a constant value of x, y, and z, so that means it is representing a point existing in three-dimensional space. Now let us do some tweaking of this equation. Now r is having some value, u is given a range of 0 to 1, and h is having a value of 20. So what does this equation represent? This thing you can just imagine that u is varying from u 0 to 1. You can put the values of u is equal to 0. So when you put u is equal to 0, so you have r is equal to 5, though x becomes 5 and y becomes 0, because u is equal to 0, sine 0 is equal to 0, so y is equal to 0, z is equal to 20. So again, this is a point, but when you are varying the value of u from 0 to 1, you are slowly decreasing the value of x and increasing the value of y until again you come at a point where again the x values go on the negative side and y value also goes on decreasing, and this is basically the representation of a circle like this. You are starting from say this is your coordinate axis, you are starting from somewhere from here, going like this and coming to the start point again when your u value becomes equal to 1, because this is now representing 360 degrees. So 360 degrees is nothing but equal to 0. So this is, what does this equation represent? This represents equation of a circle located at a height of 20 units from the xy plane. Okay. Now let us do more tweaking with this equation. Now instead of having a constant value of h, you have the h value which is starting from 0 and ending at 20. Now you have a circle which is, because h is equal to 0 initially, you have a circle which is at the xy plane, and you are moving slowly moving this circle towards h is equal to 20, that means along the z direction. So this will represent equation of a cylindrical surface starting from h is equal to 0 and going up to h is equal to 20. Let us do more tweaking with the same equation. Instead of r having constant value of 5, now you give it a range of 0 to 5. So you can very well imagine that when r varies from 0 to 5, the circle this is now representing now this is covering the whole of the area from r is equal to 0 to r is equal to 5, and this is nothing but the set of concentric circles which is starting from having a center point at 0 0 and going up to with a radius of 0 and going up to a radius of 5. So it is a continuous variation or locus of a circle with varying radius, and on the other hand it is varying the height also, that means it is nothing but a solid cylinder. Okay, now let us do more tweaking with the same equation. Now in this, instead of having r value varying from 0 to 5, you have r varying from 4 to 5. Now instead of having this is again a set of concentric circles but starting from r is equal to 4. So from 0 to 4, r is equal to 0 to 4, there are no concentric circles. So that means the space is empty. So this is nothing but representation of a hollow cylinder. So because rest of the things are the same. So this is how we can make use of the same parametric equation to represent different entities, whether it is a point, it is a circle, it is a cylindrical surface, or a solid. Now, these are some of the features of the parametric representation. These parametric representation offer more degrees of freedom for controlling the shape of the curves and surfaces. Let us see this explicit form of this equation, where y is represented with the help of x variable, which is an independent variable, and on the other hand you have this equation where auq plus bu square plus cu plus d is representing x, and similarly you have a separate representation of y. So you can see that the number of coefficient here in this x is 4 and in this y is again 4. So that means you are controlling the equation with the help of 8 different coefficients. So that means more freedom is available in the parametric form of representation than the explicit form of representation, or for that matter implicit form of representation. Now in this representation, you can easily do the transformation. A lot of transformations are needed to be done when you are working with the entities in the CAD modeling software. Suppose you draw a circle with center point at 0, 0, and it is having a radius of 7. The equation is this, and the implicit equation is this for the same circle. But when you want to shift the circle from 0, 0 center to center at 4 comma 3, the equation, the parametric equation is very simple. You are just adding 4 in x and 3 in y to notate a new modified circle, or circle which has been shifted. But if you see this equation of the implicit equation, this is a little complex than this one, and this shows that the transformation in using parametric equations is very easy. Now, in this, you have another advantage, which is representation of curves and surface segments. Because in engineering applications, we are always dealing with products which are having finite boundaries or finite limits. That is, if you are, say, designing a something cuboid, it has its corners which are well defined. But as you can see that the representation of lines like y is equal to mx plus c, which we have been doing in the you have been doing in the previous courses or previous classes, it doesn't have any information about the start point and end point of the line, which is quite becomes problematic when we deal with engineering products. So here you can see that in this equation of a circle, if you this is representing a complete circle, and you can easily represent the circular arc. For example, the portion of the circle which is coming into the lying into the first quadrant can easily be notated with the help of u varying from 0 to 0.25. So that means a circular arc lying in the first quadrant. So likewise you can define the circular arc or finite limits of any of the curves. Another advantage of the parametric representation is that they are very good for handling infinite slope. For example, in implicit or explicit form of representation, the way of finding the slope is dy by dx. So you have an equation of a curve, and you differentiate it with respect to x and find out if that is answer is coming out to be infinity at a particular point. That means the slope at that point is infinity or vertical. Okay. So infinity, dealing infinity in computers, because you are all doing CAD modeling and softwares with the help of computers, and there are subroutines which are working for you in the back end. It is very difficult to handle this term infinity, because the moment you divide something with zero, it becomes almost incomputational or uncomputational. So parametric representation helps us to define the infinite slope in a computer friendly manner. Like in this case, you have to just say that dx by du is equal to 0. That implies infinite slope. So this is very simple. Zero can be handled very well by the computer. Excuse me. So parametric representation, they have an advantage in calculation of points for display and toolpath. For example, this circle, you can find out this point, any point on this circle by defining different u values. Like I can say u is equal to 0 is this point, u is equal to 0.1 is say this point, u is equal to 0.2 is this point, u is equal to 0.25 is this point. So I can divide the circle parameter, for example, in this case, to different to n number of points for my convenience of handling or accessing the information, relevant information about this point. For example, I want a tool to move from this point to this point, so I can say I can find out this point with the help of parametric equation and this point, and direct my tool to go from this point to this point. So this way it is very advantageous to calculate points for display and toolpath. So these are the kinds of parametric curves which are you can classify that into plane curve and space curve, just like a circle or a helix. Circle is a plane curve and helix is a space curve. You can have non-form of curves and free-form curves, like circle is a non-form, and basic curve, which we'll be discussing in one of the lecture, is a free-form curve. We'll see in more detail what these types of curves means. And similarly, you have interpolation curves and approximation curves. Interpolation curves is when you have the data points and the curve passes through those data points, touching those data points. Then you call it as interpolation curve, and Hermite curve is an example. You'll be discussing in one of the lecture. And approximation curves, when you have some data points you want to, or the control points with which you want to draw a curve. The example of control point is like start point and end point of a line are the control points of a line, or center point and any point on the perimeter is the control point of a circle. Just to give, but free form curve, the user is free to give the number and extent of control points or the location of control points. And Bezier curve is another type of free-form curve which approximates the control points. It doesn't goes through all the control points, but fairly approximates the given control point. So we'll be discussing in detail about these different kinds of curves in our lectures, and this is these are the parametric representation of a line. You can note this down. X is equal to x1 plus x2 minus x1 into u is the parametric equation for x coordinate of the line. Then similarly, you have parametric equation for y coordinate of the line, where x1, y1 and x2, y2 are the start point and end point, and u is the parameter starting from 0 and ending at 1. So typically 0 here means the start point. When you put u is equal to 0 in this equation, you get x1 y1. Put u is equal to 1 in this equation, you get x2 y2. Okay, so this is the start point, this is the end point. And in space, similarly, you have another coordinate which is the z. The representation remains the same. This is the parametric representation of a line, and here you have the parametric representation of a circle. You can have like x1 y1 as a center point and r is the radius, and you can either take the parameter theta, or more convenient form is the u, 2 pi u. So u varies from 0 to u 0 to 1. If you are taking this, then you have to say that theta varies from 0 to 2 pi. Here you can say that u varies from 0 to 1. So this is one and the same thing, but I find this one more convenient because you are here representing with number 0 to 1. So as I discussed in previous one of the previous slides, that when you say u is equal to 0, this is this point on the circle, and it goes from this as you increase the value of u is equal to half here, and when you say u is equal to 1, it coincides with the first point, and this is u is equal to 0.25, this is u is equal to 0.75. Okay, and this is very easy to represent circular arc. In this case, for example, you want to represent, say, this to this point, so you can say u is equal to 0 to u is equal to half, sorry, 0.25, and here you can say u is equal to 0.75 to u is equal to 1. So you can define, likewise you can define any curve, like from segment from this point to this point, or even this point to this point. So you have to find out the appropriate u value to define that segment, and write it along with the equation. Okay, and these are the parametric representation of conics, which are second degree equations, ellipse, parabola, and hyperbola. Okay, and there are free form curves which we will be discussing in the course of in this course. You have the parametric cubic curves, or also called Hermite curves, and there are approximation curves like Bezier, B-spline, and Knobs curve that we will be discussing. Thank you.